The geoduck are especially long-lived bivalves, and the longest that we know of in the Northeast Pacific. They can get to be over 180 years in age in parts of their range. That length far, far predates any instrumental records of temperature or biology in the region. They can live a very long time and form very clear growth increments, just like a tree does. So these geoduck allow us to generate multi-centennial histories that can be very helpful in getting a solid climate record. The general name for what I do with marine organisms and freshwater organisms is sclerochronology. Sclero for hard parts and chronology for time. Just like dendro is for wood and chronology for time. It's a developing field, and it's wonderful to see more and more labs opening up as the power of these techniques becomes realized. We apply the most fundamental techniques of dendrochronology to the growth increments in these organisms, and specifically this process of cross-dating, which ensures that we can get a year-by-year or annually resolved history back through time, which is very important when we want to relate these chronologies to climate. And here's a really conspicuously wide and presumably warm year. And so by doing these growth increment chronologies, we provide a shortcut to this long-term sampling. And it's the tree ring techniques that allow us to get the exact dating. And this technique of cross-dating has been around since the inception of the Laboratory of Tree Ring Research here at the University of Arizona. And it's really this cross-dating technique that distinguishes dendrochronology from other paleo environmental techniques. And it's that year-by-year history we want to develop for the marine chronologies, because then you can seamlessly integrate those marine chronologies with environmental indicators, the marine chronologies with one another, and even the marine chronologies with tree ring chronologies on land to establish linkages across the marine terrestrial ecosystems.
The darker bands are the organic rich segments.
And turns out that geoduck growth increment width is a wonderful indicator of temperature. So they're really like living thermometers. And when we generate these chronologies, we can develop these 100+ year histories of temperature. And then go back to these sites and collect dead individuals and append those to the live collected individuals to go back multiple centuries. And that's a major project that my lab is involved in right now. And then we can compare those geoduck chronologies to tree ring chronologies on land and see how they both corroborate one another to provide a more robust history of climate than either archive could provide alone. And I'm pleased to be in a position to try to facilitate that.